Hold on to your hats, folks, because today we are going deep.
Deep.
Yeah, deep into one of the most game-changing scientific papers ever.
Really? Ever written?
I think so. It's Einstein's 1905 on the electrodynamics of moving bodies.
Ah, classic.
And we're not just dealing with equations here. This paper, it shifted how we understand space and time.
And light, don't forget light.
Oh, yeah, the light itself, the whole shebang.
What's wild is how Einstein starts with a pretty simple question.
Simple how?
Like, if physics is supposed to be universal,
Right, the laws are the same everywhere?
Exactly. Then why do they seem to, break down when things start moving?
Okay, my brain is already doing loop-de-loops. Can you give me an example?
Sure. Imagine a magnet and a conductor, like a copper wire.
Okay. Yeah.
Move the magnet near the wire, what happens?
You get an electric current, right?
Bingo. But you also get the same current if you just move the wire, keep the magnet still.
So it's the same result, but...
The classical explanation for why is different depending on what you consider moving.
Is the universe messing with us?
In a way.
It's like physics has different rules depending on where you're standing.
That's the puzzle Einstein was grappling with.
You didn't like that, huh?
Nope. He couldn't accept that the explanation changes just because our viewpoint does.
Makes sense.
Plus, back then, scientists were trying to find this luminiferous ether.
What's that?
They thought it was what light waves traveled through, like a medium.
Oh.
But they couldn't detect it, so Einstein had this radical thought.
Let me guess. He was like, what if everything's moving?
Pretty much, he said, what if there's no absolute rest?
Whoa, hold on. Everything's moving relative to something else then.
Exactly.
But how can we even understand the universe if it's all just wibbly-wobbly motion?
That's where Einstein's genius comes in. He introduces two postulates.
Postulates, fancy word.
Basically two statements, kind of simple, that are the foundation of his special relativity theory.
Okay, hit me with number one.
Number one is, the laws of physics are the same for all observers moving uniformly.
So on a train or standing still, physics works the same.
Yep, but postulate two, that's the real kicker.
Okay, lay it on me.
The speed of light in a vacuum, it's the same for everyone.
Everyone.
Yeah, no matter how the light source is moving, you always measure light at the same speed.
Wait, even if I'm chasing a light beam at warp speed?
Even then, it'll still be that same constant speed.
No way. That just seems impossible.
It does, based on what we're used to, right?
Totally.
But Einstein realized if light speed is truly constant, then our ideas about space and time,
They gotta be wrong.
they can't be absolute, they have to be flexible.
So to make the math work, he had to bend our reality.
He had to break it open.
And what came out of that crack?
One mind-blowing consequence is the relativity of simultaneity.
Big words. Break it down for me.
It means two things happening at the same time for one person might not be simultaneous for someone else moving differently.
Okay, now my head is spinning. Need an example.
Picture this, you're on a train platform.
Okay, I'm there.
Two lightning bolts. They hit the ground at the same time, one in front, one behind you.
I see both at the same time. Makes sense.
But someone's on a train moving fast past you.
Okay, they're zooming by.
Because they're moving toward one bolt's light and away from the others, they see them hit at different times.
So just because of their motion, their now is different from mine.
Exactly. It messes with how we think about time.
Time isn't absolute then.
It's relative to your frame of reference. Einstein showed that.
So how do we even measure time and space if it's all relative and stuff?
That's where these things called Lorentz transformations come in.
Heard of them, but not sure I get them.
Imagine you could shrink a ruler just by making it go really fast.
Now that's cool.
That's length contraction in a nutshell. And these Lorentz transformations are how we calculate that shrinking. They also let us figure out how time slows down for a moving object called time dilation.
So someone's in a spaceship going super fast past me.
You'd see their clock ticking slower than yours, and their ship would look shorter in the direction of travel.
That's crazy.
It's real and more noticeable as you get closer to the speed of light.
Not just theory, huh?
Time dilation. We've measured it with clocks on airplanes and satellites.
They run slower up there.
A little bit, just like Einstein predicted.
Wow, so astronauts age slower.
Tiny bit. Yeah, it's mind-bending stuff, but we're still trying to solve that original puzzle, remember?
Right, the magnet and wire thing. Why does physics act weird when things move?
We're getting there.
Okay, so time and space, they're relative, not some fixed things.
Right.
But what about that magnet and conductor? Does Einstein finally explain the electric current thing?
He does, and it's pretty elegant.
As so.
Remember, the old way, the explanation depended on if the magnet or the wire was moving.
Right, different viewpoints.
But with relativity, that difference doesn't matter anymore.
Because motion is all relative.
Bingo. Einstein shows that when you apply his theory to, like, the equations of electromagnetism,
Yeah.
it all clicks. You get the same explanation for the current, no matter what's considered moving.
So, no more inconsistency.
Electromagnetism follows the same rules for everyone, regardless of motion.
That's satisfying.
And it's not just electromagnetism. All of physics, light, gravity, the laws are the same for all observers moving uniformly.
That's huge.
Speaking of light, Einstein deals with some weird things that happen to it when things are moving.
You mean like the Doppler effect?
Yeah, an aberration.
Those always trip me up.
They're brain benders, but Einstein clarifies them.
Okay, how?
Think about an ambulance siren.
Gets higher pitched coming towards you,
Yeah.
lower going away.
Because the sound waves get compressed or stretched, depending on the motion.
Right, makes sense.
Same thing with light waves, star moving towards us.
Light gets compressed, bluer.
Away from us, stretched, redder.
That's how astronomers know if galaxies are moving towards or away from us, right?
Exactly. But here's the cool part.
Okay.
Since light speed is constant, the way light waves shift is different from sound.
Different how?
This difference, you could only explain it with Einstein's relativity.
So even light's behavior backs him up.
100%. Then there's aberration.
That's where stars' position seems to shift, because the Earth is moving.
Yeah, like running in the rain.
Rain's falling straight down, but you gotta tilt your umbrella.
Perfect analogy. Because we're moving, starlight seems to come from a slightly different place.
And this, again, it's because light speed is constant.
And you got to factor in relativity. It all ties together.
It's amazing how it all connects back to Einstein's ideas.
The power of his theory, but we haven't even gotten to the most famous part yet.
You're talking about Eames-She-5?
One and only.
The equation that, like, redefined energy and matter?
Came from a later paper, but
But it's rooted on the electrodynamics of moving bodies.
absolutely. And it says something incredible. Energy and mass, they're not separate.
Wait, they're connected?
They're like two sides of the same coin.
You mean energy can become matter and vice versa?
That's exactly what efficiency means, and the soft part.
Speed of light squared.
Tells us how much energy is in even a tiny bit of matter.
So that's why nuclear stuff releases so much energy.
They're converting a little mass into a ton of energy.
And that's what powers the sun.
And other stars, fusing hydrogen into helium, releasing huge amounts of energy,
Thanks to Eames-C.
all thanks to Einstein. This equation, it's like a key.
To understanding nuclear power, stars, the whole universe.
And it wouldn't exist without on the electrodynamics of moving bodies.
Einstein changed how we see the universe, and we're still figuring it out.
Mind-blowing stuff takes a while to digest.
Definitely. Even Einstein himself was surprised by some of it.
Like black holes.
He didn't like those at first,
He
right?
thought they were too weird to be real.
But now we know they exist.
And they're even weirder than he imagined.
The universe loves to surprise us.
The more we learn, the more we realize we don't know.
Makes it exciting, though, right?
Absolutely. But before we get too lost in space, let's go back to some examples from the paper.
Concrete examples help to understand the abstract stuff.
For sure. Like his train thought experiment.
To explain the relativity of simultaneity,
Exactly.
it involves lightning, right?
2 lightning strikes, hitting the ground at the same time.
Someone standing midway between them, they see it happen simultaneously.
Right. But someone on a train, also midway, moving past.
They see it differently.
Because they're moving towards one flash and away from the other.
They'll see one strike first.
So, not simultaneous for them, shows how time is relative.
Simple but effective. What about his thought experiment with the rigid sphere?
The one about length contraction?
Yeah, if the sphere is going super fast,
Close to light speed.
it looks squished.
In the direction of motion, like it gets compressed.
It's like a cartoon character stretching out when they run.
But opposite, compressed. And it's not just a visual thing.
It's a real effect.
Did you know a clock at the equator runs slower than a clock at the pole?
Seriously.
Because Earth is rotating, equator moves faster, time dilation makes time a tiny bit slower there.
Relativity is affecting us all the time.
Crazy, right? And it gets even wilder when you think about how velocities add up in relativity.
How's that?
Classically, you just add them, train going 60, you throw a ball forward at 30.
Ball's going 90 relative to the ground.
But in relativity, you can never reach the speed of light just by adding speeds.
No matter how fast you go.
You'll always be slower than light.
Why is that?
As something gets faster, its mass increases. As it approaches light speed, the mass approaches infinity.
Meaning?
You'd need infinite energy to actually reach light speed.
So it's like a cosmic speed limit.
The ultimate limit, nothing goes faster.
Einstein really messed with our ideas of motion, but he also talks about specific examples in electromagnetism, right?
For sure, like electromotive force.
Okay, remind me what that is.
So a charged particle moving in a magnetic field.
It experiences a force.
That's electromotive force.
But isn't that like basic electromagnetism?
What's cool is you can explain this force in two ways. One way, classically, the force is from the moving charge interacting with the magnetic field.
Okay.
But with relativity, the force comes from the electric field that appears when you transform the magnetic field into the moving charge's frame of reference.
So, different perspectives, but the same result.
Relativity gives us a new way to describe the universe.
And this new language, what does it tell us?
One big thing, the energy and frequency of light, they change based on the observer's motion.
How so?
Imagine light hitting a mirror. If the mirror is still, light bounces back, same energy and frequency.
Okay.
But if the mirror is moving towards the light source,
The light hitting it will have higher frequency
and higher energy.
because the mirror is compressing the light waves.
Right, and this you can see it whether you're moving with the mirror or standing still.
So it's not just an illusion.
It reveals radiation pressure.
Light can push on things.
Exactly, like solar sails.
Using sunlight to push spacecraft.
Einstein's ideas, even the abstract ones, they have real-world applications.
From one paper, we've learned so much.
Einstein's impact on physics, technology, even our place in the universe, it's immense.
Makes you think. It's crazy to think we've only just dipped our toes into this paper.
Right.
Like, we could spend another hour talking about radiation pressure alone.
There's so much there.
But before we go, there's something that caught my eye.
What's that?
At the end, Einstein thanks his friend, M. Besso.
Oh, yeah.
He even says the whole paper wouldn't exist without Besso's help.
Loyal assistance, he calls it.
It's a good reminder that even Einstein, a genius, needed collaboration.
Everyone needs a sounding board.
I wonder what their conversations were like.
Must have been amazing brainstorming relativity.
Okay, let's sum up key takeaways for our listeners.
Okay.
If they remember just a few things from this deep dive,
Shoot.
what should they be?
Number one, Einstein blew up our ideas of absolute space and time.
They're not fixed.
Motion is relative. How you measure time and distance depends on you.
No universal clock, then.
Nope, your now might not be the same as mine.
And that's because the speed of light is constant.
For everyone, the ultimate speed limit.
And that leads to time dilation, length contraction, all that wild stuff.
Right. Time slows down for moving objects. They appear shorter.
Imagine watching a spaceship zoom past, close to light speed.
The astronaut's clock would seem slower. The ship would look squished.
And then there's EMC.
The most famous equation.
More than that, it's a revelation.
Energy and mass, interchangeable. Two sides of the same coin.
Meaning?
Nuclear power, stars, all comes down to that equation.
Awe-inspiring, but kind of scary, too.
The power locked inside matter, it's incredible.
From one paper published over 100 years ago.
Einstein's impact is still felt today.
It makes you wonder, how does all this change how you see the universe?
Yeah, how does it change how you see your place in it?
What new questions does it spark for you? Think about it. That's all from us today on this deep dive into Einstein's world.